this video we're going to take a look at how work, energy, and then momentum come into play here when we're dealing with rotating objects. So first, let's look at an object that has some axis of rotation here at the center, and we're pulling a rope along that. So think of just some simple pulley. And so the force that we're exerting on this is going to be the tension in the rope, but that's going to exert over some length s. And we know work is equal to the force times the displacement, and this displacement here we know is the arc length, so that's r theta. And the force, that F times r, we recognize that to be the torque, so we can conclude that the work done by rotating an object is equal to tau times theta, or the torque times the angle through which we rotate, which should make sense in that work is typically a force times a distance, and this is a rotational force times a rotational distance. So it remains true with our previous relationships and equations. So the definition of rotational work is that the rotational work done by a constant torque in turning an object through an angle is the tau times theta, or the torque times the angle through which it rotates. Now the angle must be expressed in radians, and then our final result, our work, is in joules. So let's say we have an object that we're rotating. We can also say, well, if it's moving, it has to have some type of kinetic energy. And so kinetic energy we know is 1/2 mv squared. Well, that tangential velocity here is just r omega. So we substitute that in, we get 1/2 mr squared omega squared. But wait a minute, we should recognize what that mr squared is. And we see that that mr squared is really our moment of inertia right there. So we're left with a result of 1/2 I omega squared for the rotational kinetic energy. Now once again, think back to kinetic energy in a translational sense. It's 1/2 mass times velocity squared. Well, this is 1/2 times rotational mass times rotational velocity squared. So it's the same concept. We just have to translate into the angular sense. So the definition of kinetic energy is that the rotational kinetic energy of a rigid rotating object is 1/2 I omega squared. Now keep in mind that I is a little sticky there. It could be a couple different things. If we have these two masses, like what we have in the picture here, we're just adding up m times r squared. We add those two products together. However, if it's a disk, then we're going to use the equation from the table. If it's a sphere, a spherical shell, we'll use the equation from the table. All those things come into play here. And one of the requirements here is that we must have it in radians per second, the angular speed, and once again, our energy is measured in joules. So let's take a look at an example here where we have a thin hollow cylinder, so that we're going to call mass h and a radius of rh, and a solid cylinder of mass s and a radius of rs. And they start from rest at the top of an incline. We want to determine which cylinder has the greatest translational speed upon reaching the bottom. So which one's moving the quickest down at the bottom here? Well, in order to do that, we have to examine the energy that it has at the top and the energy that it will have at the bottom. So let's look at the energy here. And we know that the total energy will equal the translational kinetic energy plus the rotational kinetic energy plus the gravitational potential energy. So we look at what does it have at the top and what does it have at the bottom. And we know energy is going to be conserved because there are no outside forces acting on this. And we are going to look at the energy it has at the beginning will equal the energy it has at the end. So all of its final energy will equal all of its initial energy. And looking at this, we can cancel a few things out in that initially it is not rotating nor is it moving translationally. So that's gone, and in the end, it has no potential energy. So we know that this omega here, the rate at which it rotates at the end, we can express that as the final velocity divided by r, because using our rolling motion techniques here, knowing that this is rolling at some speed vf, we can find the rotational speed omega by dividing by the radius. So using that, we can then substitute in vf. Now we have vf in both of our terms. And we can solve for vf to be 2 mgh, that initial height that we have, over m plus I over r squared. Now, the cylinder with the smallest moment of inertia will have a greater final translational speed, because the smaller this is, the bigger this will be. And so we have to look at, well, which one has a smaller moment of inertia? And this is where we want to look at our tables to see that, hey, the cylinder, the solid cylinder, has a smaller moment of inertia than the hoop. So if an object that rotates can have energy because of its rotation, then that same object can also have momentum. And so the definition of angular momentum is that the angular momentum, and we're going to use the letter L to signify the angular momentum, the angular momentum of a body rotating about a fixed axis is the product of the body's moment of inertia and its angular velocity with respect to that axis. So this is L is equal to I omega. But once again, let's go back to our translational definition of momentum. Momentum P is equal to m times v, a mass times a velocity. Well, this is a rotational mass. This is a rotational velocity. So we're just doing the same thing we've done before, just with our new symbols here and our new quantities describing the rotation. Now, the angular speed must be in radians per second, just like it needed to be in the energy equation, and our moment of inertia needs to be in kilogram meters squared per second. So the principle of conservation of angular momentum is kind of similar to the principle of conservation of linear momentum, except they are conserved separately. Okay, they both are conserved, but they are conserved separately. And so the angular momentum of a system remains constant, or in other words, is conserved, if the net external torque acting on the system is zero. Now, one of the easiest ways to see this is, and we've all experienced this, if we have an ice skater that's spinning, and she's spinning at a certain rate, so she has some omega, and then all of a sudden she brings her arms and legs in tight. We notice that she starts to spin faster. And so this is a demonstration of the conservation of angular momentum, because when her arms are out, she has a higher moment of inertia. She has more mass away from her axis of rotation. When she brings them in tight, her moment of inertia decreases, which causes the angular velocity to then increase in order to keep the product of the moment of inertia times the angular speed to be constant. So we can use the conservation of angular momentum to explain why we notice a change in rotation of this ice skater when she pulls her arms out and brings her arms in. Now, this also works when we're dealing with satellites around either Earth, or Earth as a satellite around the Sun. And so we know that all planetary orbits are elliptical, and some are very close to circular, but they're all some type of ellipse. And so that means that there is some perigee where we're the closest to our body that's at the center, and the apogee where we're the farthest away. And so in those, we know that when we're closer, we have a higher speed, and when we're farther away, we have a lower speed. And once again, this is conservation of angular momentum of this body rotating around some central body. So our angular momentum at each point is going to be constant because we have a bigger radius. That means a bigger moment of inertia. That means we need to have a smaller speed. So when we have a smaller radius, smaller moment of inertia, we need a bigger speed. So let's look at this example. We have an artificial satellite that is placed in elliptical orbit about the Earth, and its point of closest approach is 8.37 times 10 to the 6th meters from the center of the Earth. And it is at its greatest distance at 25.1 times 10 to the 6th meters from the center of the Earth. The speed of the satellite at the perigee is going to be 8,450 meters per second. We want to find the speed at the apogee. So that's looking for, what is this VA? Well, knowing that our angular momentum has to be constant, we can use that conservation principle. So knowing that angular momentum is I times omega, we can say that it's going to be conserved. So the IA omega A is going to equal IP omega P. Well, we know that this I here is just mr squared, and omega is just V divided by R being the radius or the distance from the center. So we substitute those in, and we're left with this expression here. Now, doing a little bit of algebra, we can cancel some things out and say that, all right, those masses are going to go away because it's the same mass at either point. and we can rewrite things to say that this is just RV times RV. And so in solving, we get the VA, the V at the apogee, is going to be RP times VP over RA. Plug those numbers in, and we see that we have a speed of 2,820 meters per second. We can use the conservation of angular momentum to help find the speeds in this elliptical orbit. And in fact, it is the principle of the conservation of angular momentum that proves Kepler's second law to be true, in that sweeping out the same area in every time interval is actually just restating that the angular momentum is conserved.